In the previous video, we were looking at the types of fusion that occur in main sequence stars that allow hydrogen to be fused to form helium. We're now going to have a look at the lifetime of main sequence stars, and I want to preface this by first of all saying what I'm going to go through here, the steps are things that you need to be able to understand and make sense of. They're not necessarily steps that you will have to reproduce exactly as I do them here. So it's one of those ones where in the syllabus it doesn't specifically say that you have to be able to demonstrate this. You just need to make sense of how you can use this relationship to look at the lifetime of main sequence stars. So if we consider a star, it might sort of seem that if you have more mass, that because there's more mass it's going to last longer. So it sort of makes sense. Stars with more mass would have a longer lifetime. There's more of it there that would mean it would exist for longer. But in fact it's the opposite. And the reason for that is due to luminosity of the stars. So when considering luminosity, the opposite is actually true. So more mass results in shorter lifetimes. So the rest of this video is basically looking at that relationship and why that is so. And to start with, we need to go back to subtopic D.2, where we looked at the relationship between luminosity and mass, where L is proportional to m to the power of 3.5. So L being the luminosity and capital M being the mass of the star itself. Now for luminosity, it's basically just a measure of power, really. So luminosity is given by the equation L is equal to E over T, where L is the luminosity, E is the energy radiated. So the total amount of energy radiated by the star, and T is the time for which hydrogen is being burnt. So time for which hydrogen is fused. But if we consider radiation, when we're dealing with radiation, basically it's going to mean that when that energy is radiated, so the radiation of energy is actually going to be coupled with a loss of mass. So we don't have energy just coming out of nowhere. It's going to be coupled with a loss in mass of the star. And if we consider the mass of the star being capital M, there is a proportion of the star that's going to have been radiated as energy. So if we look at that proportion, so for a star of mass M, it's going to lose. It will lose mass. Get that right? It will lose mass given by the expression K to M, where K is the proportion of mass that's been radiated. Proportion of mass lost. So let's say, for argument's sake, that it was only 0.05% of the star was being radiated as energy. Then what did I say? 0.5%. Then it'd be 0.005 would be the value of K. So it's just the proportion. So that value of Km is actually going to be quite small. But that is going to correspond to a certain amount of energy. And we can figure out how much energy that corresponds to using Einstein's equation, and that equation being equals mc squared. So because the mass that's being lost here is km, so E then is going to be equal to km multiplied by c squared. And if that's the amount of energy, we can then say that the luminosity would be given by km c squared over tau, and we're going to use tau here to indicate the lifetime of the star. So the total amount of energy that's being lost corresponds to the energy being radiated over the lifetime of the star. And rearranging that, we can then express the lifetime as kmc squared on L. Now, in this case, we don't know what k is, we don't necessarily know what m is, but we know that there's these proportional relationships. So we can identify that tau is going to be proportional to the mass of the star. C and k are constants, so we could say it's going to be proportional to m over L. But we already know that L is proportional to m to the power of 3.5, so we can then write that tau is proportional to m over m to the power of 3.5, and simplifying that one last step, tau then is proportional to m to the power of negative 2.5. Now this is not an equation in the data booklet, it's just a relationship that where you can show how the luminosity of the star relates to its mass, and also relates to the time, the lifetime of the star, and so we can combine those two to show that the lifetime of the star is actually going to be related to its mass. And notice it's the power of negative 2.5, so that's 1 over n to the power of 2.5, so there's an inverse type of relationship here. More specifically, the syllabus refers to comparing the lifetimes of main sequence stars to that of the Sun. So if we're going to compare to the Sun, we're looking at how the lifetime of a star compares to the lifetime of the Sun, and the notation that we use there is that circle with a dot in the middle. So that ratio will be the same as the mass of the star over the mass of the Sun to the power of 2.5, negative 2.5, sorry. So there's a relationship that we can now sort of compare any star to the Sun. So if we look at an example, let's imagine we have a star with 5 solar masses. So 5 solar masses being 5 times the mass of the Sun. So that basically means it has 5 times the initial amount of hydrogen as the Sun. So that means it's going to have more hydrogen there, but being larger, it's going to also have a greater luminosity, so it's losing energy or radiating energy at a faster rate. So that's 5 times as much as the Sun, and so for its lifetime we can see that it's going to be brighter, but it's going to burn for a shorter amount of time. So looking at that that relationship tau over the lifetime of the Sun being equal to m over m to the mass of the Sun to the power of negative 2.5, that mass that we're really substituting in there then, what we're really saying here is that we're looking for the how the lifetime of this star compares to that of the Sun. So we can substitute that as 5 times the mass of the Sun, and you can see there that the value of the mass of the Sun is going to disappear. Well, these two values here do not disappear, they cancel out, and so we're left with the value of 5 to the power of negative 2.5, which is 1.8 by 10 to the negative 2. So that's a proportion. That's shows the fraction of the Sun's lifetime that would equate to the lifetime of this particular star. Now, the Sun's expected lifetime is 10 billion years. So that's so 10 billion years is, if we express that in scientific notation, would be 10 to the 10 years. So that means that this particular star, if we multiplied that out, so basically multiplying 1.8 by 10 to the negative 2 by 10 billion, that's going to be 1.8 by 10 to the 8 years, which seems quite a long time. But if we consider the proportions or the percentages, it's going to live, or lives in inverted commas I suppose, for only 1.8% of the lifetime of the Sun. So the Sun's actually going to be around quite a lot longer than a star that has 5 times its mass. So, like we said, the more massive a sun, the more massive a star, the shorter its lifespan, and in some cases it can appear significantly shorter than, say, the lifetime of the Sun. If we went to stars that were, say, even bigger, 10 or 20 solar masses, then you're going to see that lifetime would decrease again even more. On the flip side, a star that's got even less mass than the Sun's going to have an even longer lifetime. So like I said at the beginning, this is not something that's necessarily equation-based. It's more having an understanding that due to the luminosity relationship, energy being radiated at a faster rate means that the star is actually going to sort of burn out faster and will therefore have a shorter lifetime.